Yeah, so in the last video I was doing the calculations for checking whether these two vectors are independent or not. So what I can do is, over here one of the value was 1, the other was -2. Okay, so -2, and then what I will get is 1 minus 4 is -3, and -1 plus -1 minus 4 is -5. Which is the same as this third vector. So if I take this third vector on this left hand side, so it will be exactly 3, 5. Otherwise it's -3 minus -5, because it is on the right side of the equation. So which shows that these two vectors 1 minus 1 and 2 2 are dependent. Okay, so now let's check example again. This time I am going to take 3 component vectors. 1 minus 1 1, and 2 minus 1 0, and 0 minus 1 2. So we want to determine whether these 3 vectors are linearly independent or not. So the easiest, most direct way to determine is to convert them into an augmented matrix. 1 minus 1 1, 2 minus 1 0, 0 minus 1 2, and then apply the row operations. So I apply the row operation, row 1 plus row 2, and then that will be row 2, and then row minus row 1 plus row 3, that will be row 3. So by doing this, so it will be 1 2 0, 0 1 minus 1, and then 0 minus 2, and then 2. Now apply another row operation. So make this as 0. So 2 row 2 plus row 3. So now I will get 1 2 0 0 1 minus 1, and it will be 0, and then 2 plus minus 2, that is 0. So it will be -2 plus 2 is 0. So in this case I can see that the last row becomes 0. The last row becomes 0. So which will mean that we can always find a solution in terms of the free variable, okay, for this set of equations. Okay, we have done it many times before, because now in this case what we have now is 3 variables, x1 x2 x3, and then 2 equations. So we can always choose x3 is equal to a free variable s1, and then other 2 solutions will be in these 2 terms. So which will mean that we can always relate these 3 vectors with some arbitrary constants and scalars, and then that means that in this form, when we get it, so we get a echelon form, of course, but in this echelon form last row is 0. This will mean that we can always relate these 3 vectors by some linear combination, okay, with arbitrary values of s1 s2 s3, which may not necessarily be 0, or they can be other than 0. So if this is the case, then these three vectors are linearly dependent. Okay, so I think this much proof is enough, or otherwise if you want more, then of course we can find the solutions in terms of S1, and then these three solutions in terms of S1 we can incorporate as their multiplication, and then we can add together, and then we can see by ourselves that uh, our final result will be having it a linearly dependent result. Okay, I solve one more example. Example 2. So suppose if I have a matrix A, 1 minus 3 0 and 2 6 1 and minus 5 0 4, and I want to determine that whether the columns of these of this vector, three columns of these vectors, are linearly independent or not. Okay, so determine three columns linearly dependent or not. So the process is the same. Apply the row operations on this. So what I can do is I can apply a row operation 3r1 plus r2 to r2. So in this case 1 2 minus 5 0, and it will be 12, and it will be minus 15, and then 0 1 4. Next I apply another row operation. It will be actually easier if I interchange these two rows. So in this case, interchange R2 with R3. Okay, so that I will have 1 over here. So 1 2 minus 5, and then 0 1 4, and then 0 12 minus 15. Now I apply a row operation minus 12, row 2 plus row 3, that will be row 3. So I get 1 2 minus 5, and I get 0 1 4, and then I get 0 0 as minus 12, and then minus 48. This is minus 48, and then this is minus 15. So minus 48 minus 15 is minus 48 minus 63. So I get this form over here. So now in this form we can say that this is an echelon form. So for example, every column has the pivot position here, here, and here. Okay, and since every column has the pivot position, and then the leading variable is there, so this means that this type of matrix will result into a unique solution. Okay, it will result into a unique solution. So it will mean that since the solution will be unique, so it will mean that these three columns are linearly independent. So the answer is these three columns are linearly independent. independent. So suppose, for example, if we will have 0, 0, 0 over here, then we will get all those C1, C2, C3 as 0, 0 solutions, and that will be the unique solution, although that solution will be trivial, but this is the condition for the linear independence. Or if there are some non-linear values over here, then we will get some non-trivial solutions. For example, if we have a system as Ax is equal to b, and if b is equal to 0, then all these coefficients in the form of x1, x2, x3 will be 0. But if b is not 0, then we will have some independent, unique, non-trivial solutions. In any case, we will say that these three columns are linearly independent. Okay, so one more example. If we have a system of linear equations such as this, x1 plus x2 and plus 3x4 minus 5x5 is equal to 5, and then x3 minus 6x4 and plus 10x5 is equal to minus 7, and then 3x4 minus 4x5 is equal to 6. So this this system has three equations but two variables. So this system of equation will have a general solution, okay, in terms of the two free variables. So this general solution can be represented like this: x is equal to x1 plus x2, x3, x4 and x5. And in fact we have already solved this system of equation in one of our previous videos. So the answer over there was this. So and the value of x1 was minus x1, okay, it was minus 1. The value was x1 was minus 1 minus 3s1 and plus s2. The value of x2 was s1 s1, and the value of s3 was 5 plus 2s2, and the value of x4 was 2 plus 4 by 3 s2, and the value of x5 was s2. Okay, and of course this system can be written like this: minus 1 0 5 2 0. This is one vector, plus s1 minus 3 1 0 0 0, and plus s2 1 0 2 1 0 2 4 by 3 and 1. Okay, so now the question is Yeah, this I did not solve it because